Hello, everyone. My name is Jianhui Li. You can also call me Frankie. I'm from UW-Madison, and today I'm going to talk about a recent collaboration with tonal decoupling for smooth surfaces in R3. Okay, in the beginning, I'll introduce you what is decoupling. Then I'll state our main result. I'll survey a dimensional 2 case, which is done previously. And then I'll tell you how the difficulties extending from dimension 2 to 3. First, introduction to decoupling. So let me start with notations. Usually we consider manifold given by the graph of a function phi, and we'll mainly focus on R3 today. And we'll focus on smooth functions phi or smooth manifold. For any, we consider some very small delta. We consider the delta neighborhood of this manifold. And what it means is that we start with a manifold, and this is in R3, and then we consider delta neighborhood, slightly thickened delta neighborhood of this. And then this could be something like this. This is a surface, okay? And after that, taking the delta neighborhood is delta neighborhood of a surface. And what we do is we want a boundary overlapping covering of it. And it is delta thick, which means that we are considering certain covering of this type. Okay, also something here as well. And also something here as well. And the thickness is all delta, okay? And we get the partition. And what we do, we call this partition, each element tau. There are many other taus, okay? We are considering this as a frequency side. And we are going to restrict F to all these small caps tau. Okay? This can be caps. In some cases, it can be curved. So it might not be rectangular, but ultimately we want it to be rectangular. Keep in mind. Okay. So with this setting, we consider decoupling inequality like this. What does that mean? That means that we start with a Schwartz function f. We want to bound the L4 norm of this Schwartz function by each individual pieces of f restricted on this small caps tau. And we want to say how much we lose by considering this. And we want to compare it with little L2 because of the Pancherel, because if 4 is replaced by 2, and we by Pancherel, we have the little L2, big L2 decoupling. That's trivial. But in the case of some curvature, with some curvature, we can do better. We do have big L4 decoupling for R3. So we'll focus on 4, which we usually denote that with P. Okay. And we also say that this manifold can be LQ L4 decoupled into this small caps tau if the decoupling constant, the best constant that this decoupling works, is very small. Okay, for any epsilon bigger than 0, it is delta to negative epsilon. It is usually of size log delta, something like that, but it is subpolynomial growth. Okay. Before moving to the main result, I would like to tell you some basic properties of decoupling. And these properties will be used in the proof strategy I'm giving today. And these are some fantastic properties that make decoupling famous. And I would say, okay, the first thing is affine invariance. What does that mean? That means that starting from any affine transformation, non-singular, if the manifold M can be decoupled into smaller caps tau, then if you translate that or rescale that, because those are all affine transformations, the new manifold can be decoupled into the transformed little small caps. Okay, this is so-called affine invariance property of decoupling. And the second important property is iterated decoupling. What does that mean? So look at this inequality. You start with f on the left-hand side, and you end with f tau on the right-hand side. Imagine if each tau can be further decoupled into even tinier caps. So what does that mean is you have this is your tau. If you want to decouple it into even smaller, so for this tau, we want to do even smaller. These are all thetas. Okay, there is also a theta here. Okay, if each of the tau can be uniformly, like for each tau, the constant is the same and all can be decoupled into all these small thetas, then what it implies is that the original M manifold can be decoupled into this small caps theta. Okay, union of all this. And it is very good because you can see this from the structure of this inequality. Okay. And also, we know that little L2 is the strongest because of the Holder's inequality, and we only consider Q bigger than 2, okay, at least 2. Okay, and by using Holder's inequality on this little L PQ norm, then we get this. And finally, there's a projection property. We can project a manifold, okay, to any subspace. Then if we can decouple the manifold in those subspaces, we can decouple the original manifold. Remember, actually, this projection forget some of these geometric properties. And as I said, curvature plays an important role in this. And after the projection, a curved region can be no longer curved. So that's why if you can do something on the projected set, you can do it for the original set. Okay, and the last and very important feature I want to mention before talking about the main result is about flat or trivial decoupling. What does that mean? So there are EC bounds you can get by using Pancharel, which is a little L2, big L2 decoupling, and triangle inequalities, which is little L1, big L infinity inequalities. You interpolate it, you get something like this. Okay, note that 4/3 is the dual of 4, dual exponent of 4. And then you apply again the triangle, sorry, the Holder's inequality, and you get this. Okay. This is a trivial decoupling. We don't consider any structure at all for all the manifold, the underlying manifold, right? So we call it trivial decoupling. But on the other hand, if the manifold is flat itself, which means that the delta neighborhood of it is essentially just a rectangle, then we also have a lower bound. Okay, the lower bound is roughly speaking the same as the upper bound. Okay, what does that mean? That means that in particular, any non-trivial decoupling exists for this little L2 norm. Because when it is little L2, you remember you don't want any factors. The only admissible factor before the decoupling is delta to negative epsilon. Okay, this is a lot larger than that. Like this is when you put Q equals 2, this is like that. So unless the number of partitions is very small, if it is that small, you can use triangle inequality and to get the estimate you want. And this is not something we want, right? So only this kind of trivial partition happens for flat manifolds. So that's very important to keep in mind. So which means that to decouple the manifold, if you want to consider little L2, the only thing you can do is to decouple up to all these flat pieces. So let's look at some of the well-known decoupling results. This result will be used as a prototype of our proof. So in Bourgain-Demeter's decoupling result, we get this, they consider paraboloid, and paraboloid can be decoupled into these flat caps. You can check these are the caps, flat caps for paraboloid. We always consider truncated paraboloid. And parametric Seeger iteration, tells you that any perturbation of that paraboloid, in particular, as long as the Hessian determinant is bounded below, then it is good. So any strictly convex M satisfy that, right? Because we consider a compact set. And this flat cap, you can do a Taylor expansion. You know that it is of the size roughly this. Okay, and this depends on the lower bound of the Hessian determinant. This is a Parametric Seeger iteration. Okay, and later, a few years later, Bourgain and Demeter proved a similar result for hyperboloid. But remember, for hyperboloid, you can never get little L2 because there are strict lines on it, and strict lines are flat. So you can't decouple flat strict lines, the delta neighborhood of a strict line. So no, little L2 doesn't work, but they do have a little L4, and we'll use that. Okay, and in particular, using Parametric Seeger, any manifold with non-vanishing Gaussian curvature can be decoupled. Okay, at least little L4, but for convex case, it is little L2. Strictly convex case. Okay, these are the results we had. The major result we had. There are some notable other results, but we are not discussing here. So the question is, for a manifold with vanishing Gaussian curvature somewhere, it can vanish somewhere, of course. Can we decouple M into flat caps? Is it possible? Okay. And the answer is yes, but in R3. And this is our main result. Okay, let me write the long version or the accurate version of this. It is quite accurate already, and the slightly dishonest part is that the overlapping is not that good. Like other than this, everything here is basically from the notation, from what we say, something can be decoupled into something. Okay, and then we have this inequality. And moreover, if it is convex, then we have the little L2. And we know that for convex case, this is the best enough. The best we can do, the best we can decouple. We can't decouple further. But for little L4, or you may ask, can we do better, little L4 do better? Yeah, it is possible, but we don't know. Okay, the achievement in these two cases is similar, and I will present you soon. In fact, the first reduction we do is to change the smooth manifold to polynomial surfaces, because polynomial surfaces are easy to deal with. But in order to pass from polynomials to smooth case, we need to make sure that our estimate is uniform in D. Okay, so we can see that this estimate is uniform in D, which means that the decoupling constant here no longer depends on M, but only on the upper bound of the degree of the polynomial defining the polynomial surface. And moreover, like for the convex case, we also need a uniform like in D, which means that the decoupling constant doesn't depend on M, the manifold. And then we can use some Taylor expansion, some approximation argument to recover the smooth case. Okay, these are our main results. And now we'll move to discuss the dimensional 2 proof. I will give you a brief idea on what happens in 2D. So what happens in 2D is that any 2D curves in, like, we consider the surface in 3D, and which is the curves in R2. For all of these polynomial curves, the point for which it is vanishing, having vanishing Gaussian curvature is very tiny. We rotate it, and to make it here, exactly here, this is the place where the Hessian determinant is roughly is equals to 0. So Hessian determinant in 1D is just second derivative. Okay, and it is one-dimensional. So it is one-dimensional. So so which means that these points are isolated. By partition of unity, we just consider them like as a single point. Okay, and what we do next is to consider a dyadic decomposition. Approximately delta sigma for sigma dyadic numbers between delta and 1. Also, we consider the remaining set, which is delta. So we call this S delta and S sigma. Okay. In fact, S delta is some set near this region, as you can expect. And this S delta set can be something like this. Okay, can be something like this. It can also be this piece. Okay, this piece of the paraboloid. Okay, these are different sigmas. You give different set. This partition is fine. Why? Because the number of set here is bounded by log delta inverse. It is not too large. Do you agree? There are only log delta inverse many this kind of dyadic numbers between delta and 1. So that is the loss we can tolerate, and we just use triangle inequality or trivial decoupling to do this. Does that make sense? Okay. And then what we do is to rescale this region. Because remember, one important factor about decoupling is that it's affine invariant. We can rescale this region to this blue part to the whole unit intervals. Okay, so remember, one thing is that after the rescaling, the Hessian determinant is still roughly the same, or maybe a different dyadic number. Okay, and you know the Hessian determinant second derivative is roughly sigma prime, which means that the polynomial, like not looking at the linear terms and constant terms, those are fine, because we can do a shear transformation to get rid of them. The whole polynomial is bounded by this factor, right? So you can divide it. By dividing it, it is actually a scratching from this blue region to the new blue region. This is the rescaling in Z, in the Z variable, or the last variable, the Z variable, okay? This is scratching the interval. This interval is scratched to this interval. After doing this new, the last blue piece will have Hessian, will have second derivative bounded below, where we can apply Bourgain-Demeter. And remember, we have one property is iterative decoupling, which means that if we can decouple this blue region into smaller pieces and the red region into smaller pieces and so on and so forth, we are done. So this is how we do in 2D. And we try to generalize this idea in higher dimensions. And this is it. But there are some significant obstacles here, and I'm going to discuss about it. So the last part is the proof strategies. The first difficulty is that, let me erase this, okay? The first difficulty is that, okay, so now we know that in 1D, the set where the Hessian determinant is roughly a constant is an union of intervals, and you can just rescale these intervals to get what you want. But unfortunately, in R2, okay, the R2 case, the set where Hessian determinant is roughly sigma is no longer intervals, no longer rectangles. Like you want it to be rectangles in order to do this kind of rescaling. In fact, it can be very, very bad. It can be something like this. Okay, it can be even has some intersection, and it can be only be like, let's say, this kind of regions. Because you know, the Hessian determinant is a polynomial. Like if phi is a polynomial, the Hessian determinant is also a two-variable polynomial, and the zero set of the two-variable polynomial is like can vanish on any algebraic set, so it can be bad, right? And so it can be something like that. And this cannot be rescaled directly. Intervals, you start with interval, it is good, but this is not intervals. These are really bad stuffs. So what we do is that, okay, so now we cannot do the thing here. So we forget about the Z axis. This is the X and the Y axis. Okay, we forget about Z axis. We project it to the XY plane. because we know we can use projection for decoupling. We project this onto the red piece, and there are some curved region for that red piece. Therefore, how about let's consider decoupling on this curved region first. We want it to be rectangle, remember. Like in 1D, it is interval, it is good. Now in 2D, it is curved region, and in the combination of some weird stuff, we want it to be rectangle so that we can do rescaling. But unfortunately, it is not. So what we do is to decouple this 2D set, and it is indeed true. So the solution to this problem is by a generalized 2D decoupling, which means that now this red region is good. We can decouple this region, like this is the first rectangle we take. Okay, we can take like second rectangle here, and maybe a third rectangle here. So it is a rectangular covering, you can imagine. And then this you take some rectangle here and some rectangle here. So you decouple this region, red region, into all these rectangular sets T, such that even you enlarge a little bit, it is still roughly sigma. It is important. Why? Because by doing so, again, using the affine invariance property, we can rescale these black rectangles into what? Onto the whole unit square, right? After doing this rescaling, we see that as you can compute, the Hessian determinant of this rescaled function remain roughly a constant, okay? So we reduce the cases for which the Hessian determinant is roughly a constant over the entire unit square. And we can use iterative decoupling so that it suffices to decouple each of these small rectangles and enlarge it, make it to the whole rectangle. So we only reduce to the case where the Hessian determinant is roughly sigma. Okay. Okay. So this is how we do for the first steps. But unfortunately, there is still another thing we need to take care of. Like in the previous case, if it were an interval, you stretch it to the whole unit interval. There is only one direction. And so if the Hessian determinant is small, then you can rescale the ZS's. But now, unfortunately, in 2D, it is not the case. You can consider these two examples. The first example, there are two directions, right? One direction, the eigenvalue is 1. One direction is always sigma. And so you can't just divide it by sigma or something similar to sigma. Because by dividing it, the phi is no longer a bounded function. Okay, it could be bad. You can't just divide it. So this is the second difficulty we are encountering. And there can be harder examples like example 2. This example, you compute it, you find it is roughly sigma over the unit square as well. And you cannot do any rescaling directly on the ZS's. You already utilized the dyadic decomposition. So what can we do? So you have phi, let's say it is x squared plus sigma y squared. It is simplified models, but we'll look at it. So what we do is that, how about we project on the other plane, right? If we project on xz plane, what do we get? What we get is this, xz. What we get is this, right? Because it is sigma, roughly sigma. You project it, you forget about this term, and it becomes x squared. You see curvature when you project it in xz plane, because the y direction, like the error term, like originally the error term is delta, but now after this projection, the error term is now sigma. It is pretty bad. It is not as good as delta, but it is fine because there's something we can do. That particular something is that you have the curved region now. You use a delta scale cylindrical decoupling or the lower dimensional decoupling after the projection, and you just project this into these rectangles, okay? And these are rectangles, and you rescale this. This makes you one of the direction, the x squared direction, also small, so that you can rescale in the z-axis. Okay, so this is how you solve the second problem. It is, in general, it is a lot harder. I just tell you the simple case, but the strategy is like this. And why we can always do this is by this proposition. It tells you that whenever the Hessian determinant is small, then there always has a direction you can project it to. Okay, this A depends only on X. If you project it at Y after rotation, which is fine, it is a fine transformation. After this rotation, these factors you can project in that direction, which is of height delta to the alpha. You just consider this delta to the alpha thick approximation in the XZ plane. Then you do some decoupling if A to the X has some curvature on this. And this is how you do it. And this solves the problem in general. And yeah, and alpha, the key part is that this alpha depends only on D. Okay, and this property is uniform in the whole like unit squared. The entire thing, not a local property. And that's it. That's the proof strategies, the two main obstacles we overcome. And yeah, thank you for your attention.